Welcome to ilectureonline. Here's a very good example of how to use the superposition principle in order to solve a circuit like this. And you may want to do it like this because it makes it quite a bit easier. What we're trying to determine here is the voltage at this particular node. However, realize that this node and this node are really the same in the circuit because there's no devices in between. We are going to separate the circuit into two separate circuits. Now you say, well, wait a minute, aren't there three sources? Well, there are two independent sources. There is a voltage source here, a current source there, but there's a dependent current source, so we cannot take that out. We have to leave that in each of the circuits right there. We can remove, in this case, we remove the current source, we have an open, and here we remove the voltage source, we have a short. So let's go ahead and find V sub x in this circuit and V sub x in that circuit, then simply add them together algebraically. To do that, we're going to use the node analysis method, realizing that we're going to have a current moving in this direction. Let's call that I1. We'll have a current probably in this direction. Let's call that I2. And a current in this direction. Let's call that I3. Notice that this is one single node, so we're trying to find V sub x here. We'll do the same over in that circuit. Notice again that this is one single node. But now we have four currents entering this node. We have a current coming in this direction. Let's call this I1. We have a current probably in this direction. Let's call that I2. We have a current probably in this direction. Let's call this I3. And a current in this direction. Let's call that I4. In that case, we have four currents to deal with that either leaving or entering that node. Using Kirchhoff's rule, we can say that at the node here, we can add up all the currents entering the node and set that equal to all the currents leaving the node. It looks like we have two currents entering. We have I1 plus I3 entering, and we have I2 leaving the node. Now let's go ahead and calculate what each of those are. I1 can be calculated by taking the potential difference between here and there. That would be 25 minus V sub x, 25 minus V sub x, and divided by the resistance in between, 20 ohms, plus I sub 3. I sub 3 would simply be 0.1 V sub x, 0.1 V sub x, and that's equal to I sub 2. Again, that's the potential difference between here and here, which is V sub x, and divided by the resistance in between, 4. We can go ahead and solve that equation for V sub x because that's the only unknown in there. We're going to multiply both sides of the equation by 20. Let's do that. Multiply both sides by 20. That means we get 25 minus V sub x plus 20 times 0.1 is 2 V sub x equals 425 times 5 V sub x. Move all the V sub x's to one side. That means we have 25 is equal to 5 minus 2, that's 3 plus 1, that's 4, 4 V sub x, which means V sub x is equal to 25 divided by 4, which is 6.25, and that would be volts. We have V sub x on our first circuit. We're going to add that to the V sub x of the second circuit, so we need to do this a second time. All the currents entering would be I1 and I4. I1 plus I4 equals all the currents leaving, I2 plus I3. Now we need to figure out what each of those are. I1, that's easy, that's 5 amps, plus I4 is also easy, 0.1 V sub x equals I2. I2 would be the voltage difference between there and there, assuming this is at 0 volts. That would be V sub x divided by the resistance in between, 20 ohms, plus I3, which is V sub x divided by the resistance in between, 4. Again, multiplying both sides of the equation by 20 to get rid of the denominators, and we get the following. 20 times 5 is 100, plus 20 times this is 2 V sub x equals V sub x plus, focus on 25 times 5 V sub x. Moving everything over to one side, we have 6 V sub x minus 2, that's 4 V sub x. 100 equals 4 V sub x. V sub x equals 25 volts in this case. We have 6.25 volts here, 25 volts there. All we need to do now is add it together. V sub x total is equal to V sub x for the first circuit, 6.52 volts, plus V sub x of the second circuit, 25 volts. That adds up to 31.25 volts for the total voltage at that particular node. And in this case, I would say separating the circuit into two separate circuits and solving those individually and then adding it together algebraically seemed to be like the easiest way to do this particular problem. And that's how it's done.